Hello everyone, it's 1 p.m. Eastern and that means it's time to begin another of our CoCoRaHS WxTalk webinars. Thanks for joining us today. I'm your host Henry Regis, and my normal co-host Nolan Duskin, our state climatologist, is out traveling in western Colorado today. He'll join us again next time. Running our program behind the scenes today are Zach Schwalbe and Noah Newman, and we're coming to you live from the Colorado Climate Center here at Colorado State University in Fort Collins, Colorado. During today's webinar, we'll explore the topic of weather optics. For those who are unable to join us for the live broadcast, we'll be recording it for future viewing on our website. All of our webinar web talks are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, we're excited to have with us today an old friend of many, many years, a man who has had a lifelong fascination with anything weather-related, nearly an institution himself during his 30-plus years at the National Climatic Data Center in Asheville, North Carolina, and a native of Knoxville, Tennessee, Grant Goodge. While at the Climate Center, Grant spent 10 years supervising the quality assurance and publication of data from the National Weather Service Cooperative Observer Program, and Grant has also been a National Weather Service Cooperative Observer for 50 years. Grant's a licensed pilot with nearly 800 hours of time in the cockpit. He's been able to photograph the weather from the air and the ground, and he'll show you some of those wonderful photographs today. Some of his photographs and videos, images have been used in numerous books, magazines, and even a Nova Science DVD on lightning. I wonder, maybe you guys have seen that one out there. We'll also see many of his photos, and again, Grant has also appeared in several interviews on the Weather Channel. Welcome, Grant. We're so glad to have you here today as part of our webinar.
It's great to be here. I'm amazed with the number of people who've signed up for this.
It's really neat to see folks from all over the country interested in optics, and I'll tell you, knowing Grant over the years, he is the man to tell you about these. Back years ago when I was at the National Climatic Data Center, I remember going up on the roof of the Federal Building with Grant. Every time a storm would come in, we'd watch him and take some pictures. And, well, that's another story in itself. But let's go ahead and start our webinar today, and Grant's going to tell you all about rainbows, optics, you name it. Pass it over to you, Grant. Thanks.
Thank you. I see there's some extra information on the webinar page off to the right here. I don't know whether that's showing up for the other folks or not.
Grant, you can go ahead and there's a little red arrow that should make that disappear. Okay. If you hit that red arrow, it'll slip to the side. There you are.
Thank you much. Well, welcome everybody. It is truly a pleasure to share what I've seen in the 55 to 60 years of being interested in watching the sky. And I'm sure a lot of the things that I'll show you today you have perhaps seen, but maybe not connected, so to speak, the dots. But if nothing else, I hope that today's program will inspire you to look at the sky a few more times than what you have in the past. And if you haven't in the past, I hope it'll be a whole new revelation of fun for you. So that's my objective today, with a little bit of education about these things, but just trying to make it fun and interesting to you at the same time. As Henry says, that I've been around the block here for longer than I want to think about, and see if we can get this. Having a little trouble getting the page to. There we go. And over 32 years, I observed the weather from the location that is now on the screen. It's a stitched, electronically stitched series of 4 photos, and it's kind of compressed a bit, so the peaks of the mountains look a bit steeper than they really are. But I wanted you to see that I've always had a desire to be able to see the full horizon, and Lord blessed my wife and I to have found a piece of property in western North Carolina, east of Asheville, at 4,300 feet and put up a 75-foot tower to put the wind speed sensor and the wind direction sensor, and this picture is taken from that location. But it was also a good place to watch standing wave clouds forming over the mountains to the north, and occasionally distant southwest, but primarily to the north where Mount Mitchell resides, the highest peak east of Mississippi. And also being removed from much of the city lights of Asheville, we were able to see some nighttime events, and I'll finish up with a few of those photos at the end here. But at any rate, certainly one of the best things for viewing weather of all kinds is to have good visibility, and that was also a helpful condition of being on the higher elevations there, and to have that viewpoint and the clarity, particularly in terms of the solar beam. The cleaner the atmosphere, the brighter the bows, and the better you see. Unfortunately, in the southeast, and those of you who live in this region of the country know that we have a lot of haze particles. Pardon me. In this part of the country, and particularly during the summer months, it is photography and vision of these various elements is severely compromised. At any rate, when rain is falling, there's a real neat thing that happens with the solar beam and those drops, as we see here on a limb of a fern. Quite a bit enlarged, but you can see that they are quite spherical, not totally round as a ball, but certainly with rounded shapes, and through that interface of from air to the water and reflection in the drop and refraction or bending of light in the front side, out the back side, and come back towards us. We have a spread of the solar beam into the various colors that make white as we see it on our eyes. But certainly this spherical nature is part of what produces these wonderful colors. Now, when the bigger the drops, the faster they fall. And the faster they fall, they tend to compress and get a little flatter than they are, again, as a round ball. And that has some effects on how there's a brighter display in most cases as you get closer to the Earth, as these heavier drops are falling. So let's go ahead and step forward here and see how this color is produced. And as we can see here, as a representative ray of light comes in, is bent at the edge of the drop, of that interface between the air and the water, and it comes to the back of the drop and is reflected back towards us, because our view would be off to the left in this picture. And the red light is bent more than the blue light, and so we have a spread of color in between those two, and the distance in degrees from the original path to the path that it brings that light down to us is about 42 degrees for the red side of the spectrum, and 40 degrees of a 360-degree circle away from the original path of the light beam. So now we see a picture from a broader scale, so to speak, and down at the bottom to the left is you or me or someone looking at the rainbow. And of course, it goes without saying that we have to face away from the sun to see the rainbow, because we're dealing with the reflected light in the raindrops that are falling. And here's that angle difference again, 42 degrees away from the, as we would say, anti-solar point, which would be in the middle of the bowl. and it is displayed in a very curved pattern. If the sun is low in the sky, the higher the sun is in the sky, the flatter this bow will become. And we'll see some pictures certainly proving that. And if the sun is really too high, you're not likely to be able to see a bow at all unless you maybe stood on a stepladder. Now let's go and see, as many of you have, that there is quite often more than one bow. Sometimes you see outside of that brighter bow is what we call the secondary rainbow, and that is created by a sunbeam coming in and being reflected not just once at the back of the drop, but twice, and then coming back out. And through this interface again between the water and the air, the light is spread, and in this case the red light is reversed from the primary bow. Keep losing my dot here. And so we will see that in the photographs in just a minute. But these are about another 10 degrees away from this primary bow. But you'll also see that the secondary bow is never brighter than the primary, and that's because we lose light with each reflection. Some of this light just goes right on out the back of the drop. So here we are with a real event taken from the mountain and looking eastward, and you'll see, as we briefly discussed, that with those flatter large drops coming out of this thunderstorm cloud that's already passed by, that as they fall, the closer they get to the ground, the faster they're getting there, and so that tends to make this a brighter portion in here and over on the other side than up here towards the top. And here's the secondary bow sitting outside of that, and here we have the orange side of the beam on the outside of the primary bow and on the inside of the secondary bow, and that is again because it's undergone another reflection. But it's also weaker. And if you remember, I said some of the light goes through the back of the bow and keeps going. That's this light here, and you'll notice that it's brighter here and it's brighter out here than it is in between, because the useless, or in other words, this light in here and out here, is not helping to produce the bow since it's been lost in the back of the droplet, and so the region in between is the darkest. And the next couple of photos, I'm just going to close in on this to give you a little better view, and certainly the intensity of the colors that are present down, particularly towards the part that's reaching towards the trees and the surface of the ground. Something else that we'll briefly mention here, but show in a couple other pictures, is that through it's kind of a complicated process, but it's what we call cancellation, that of some of the wavelengths of the light actually cancel each other out to the point of where there's a little darker area on the inside of the bow here, and we will see what they call supernumeraries, or extra bows, which are pretty much mostly in the blue and the green wavelength, that will appear on the inside of the primary bow, and they can be quite spectacular when they show up. And not quite as prominent here, just a bit, but here again you see a little bit of the haze that we have in western North Carolina, and it's not a good background to show the contrast of the colors, but certainly I just never get tired of seeing them. I have hundreds and hundreds of photos, even though the colors are the same. It's fun to see. Here we can truly see one of these supernumerary repeats of the colors on the inside of this bow here, and if anybody knows their vegetation, they might have some idea of where this was taken. This is in the Serengeti in Tanzania in East Africa. My wife and I and some of the members of our church were over there on a mission humanitarian trip about 10 years ago, and I thank the Lord for the fantastic view. The visibilities and the cleanliness of the air was quite a bit less since they have less industrial activity over there. Here's one out of the north side of the Climatic Center, one of the brightest bows I'd seen in my lifetime, and was a real treat. Again, we can see a little bit of that supernumerary or repeated color inside of the primary bow. Now, we were talking about how higher the sun angle, the lower or the flatter the bow becomes. And it's kind of like if you held up a hula hoop in front of your face, and you look out from the center of that hula hoop, everything would be truly a circle and very round and complete. But if you tip that hula hoop away from you, eventually it'll be a flat line, basically. And so that's kind of what's going on here. As the sun angle rises, it's like you're tipping that hula hoop of color away from you. And of course, the reason you can't see the bottom of the hula hoop in this example is because it's down here below the level of the water and the land. And here's one from somebody, I believe, in Colorado, out in the plains there. I had this, I think Nolan may have sent it to me on an email, and a month ago my hard disk crashed on my other computer, so I'm limping along with this one here. And I can't attribute the name to the person because I can't retrieve those emails. At any rate, the primary bow is down here almost on the surface of the ground as we look, or the photographer saw it, and you can see above it the secondary bow. Really a nice photo. And this one, I do know, was sent also by Nolan, and I believe the name that he gave me, if I can pronounce it right, is the Kralls from, I think he said Kralls, from Loveland. And when he sent it to me, he says, "Have you ever seen anything like this?" And I personally have not, because I didn't have a body of water. But this is a reflective bow, both the primary and the secondary bow, off of a lake that was just behind the observer in this case. And but the colors, even though they're reflected off the lake, the oranges are still on the outside and the oranges on the inside in the real bow and the reflected of the reflected light off the lake. So it is not reversed, and so the colors remain the same. Just a beautiful photograph. And if the Kralls happen to be online, thank you very much for sharing. Now, we've gone from looking away from the sun to looking towards the sun. So nothing we see in these examples here could be a rainbow. You cannot see a rainbow if you're looking towards the sun. In this case, I think you can probably see that it's not raining either. So when some of my friends say, "Boy, I saw this beautiful bright rainbow yesterday," and I said, well, where were you looking at the time? Oh, about 45, 50 degrees above the horizon and towards the sun. I said, well, it probably wasn't a rainbow. This is still a feature of light passing through cloud droplets in this example, as opposed to raindrops. But they still do the same thing. They still bend the light. So this tells you one thing, is that this is a liquid droplet cloud and not an ice crystal cloud. And we're going to show you some that are ice crystal clouds and what can happen from them. And this effect here is called iridescence. IRRIDESCENCE. And the colors, though, can be just about as spectacular, I'd say, as raindrops or a rainbow. These are a cloud formation above some rapidly rising cumulonimbus or thunderstorm clouds. This is what we call a Peleus cap, or a piled up, or it's because the clouds are rising so rapidly that they are pushing a wake of air above them, and the sun in this particular case was just in the perfect position to produce this beautiful color in the top of that formation. Now, when these colors get close to the sun, this part of this feature we would call a corona, or the bright area around the sun. And you'll notice that we go orange to the purple to the green and then back, and these colors are repeated. And this again is that cancellation process that we're talking about that produces the supernumerary bows. But it can be just a beautiful feature. The further we get from the sun, then the distribution of the colors we saw in that first example tends to be a drop size and depth of the drops in the cloud formation itself. And just to give you a little perspective here, this I wanted to show this because it was just a beautiful event. These clouds here, this is a high-resolution satellite image over East Tennessee, Western North Carolina, North Georgia, and Alabama. This narrow geographic feature here is called the Sequatchie Valley, an Indian name for hog trough, I understand. But at any rate, Knoxville, Tennessee, where I live and I'm talking from to you today, is up here. And about 2 hours after this photo, this element of this stream of clouds came on up through here, and I went out and took some pictures. But just thought I'd give you that perspective of what it looks like from the satellite image. These whiter clouds here are cumulus, as we had northwest winds at the surface that were forming these clouds off of the Cumberland Plateau and moving them over towards the Smoky Mountains. And here's that feature about 2 hours later, and we have a very nice corona brightness. Part of that is burnt out on the sensor of the camera. That is, it's trying to compromise. So if you want to do photographs of some of these things, to get the best effect, if you can find something, a post, or sometimes you may have to put your hand up there to block out the brightest part of the disk of the sun so it doesn't compromise the exposure of the camera. But what I'm going to do now is to close in on this portion here as it began to move closer to me over the sky, and see the colors that are forming in this. And this would be about, we would call these mid-level cloud and alto cumulus. And again, because of these colors, means that these are liquid drops. Now, they may be below freezing, and this is going to sound strange to you if you're not already familiar with it, but cloud droplets in the atmosphere can be as cold as 50 below zero Fahrenheit and still be liquid. But if they're shaken or bumped, like an airplane flying through them, or they anything, wind shear, something, then they will freeze instantaneously and quite often will start falling towards the ground. But at that height, they rarely reach the ground, and that's why we call them virga. Just another couple of views. Fabulous color for me, anyway. And that's something else I'm certainly thankful for, is the ability to see color. Several of the men that worked with me at the Climatic Center were colorblind and could not tell. A rainbow to them was just a bow. Okay, now we're looking back, this case, away from the sun, and we're seeing kind of a similar effect in this these stratus clouds that are moving up the face of the mountain. This is my shadow here in the middle, and around there is this bright area where the sunlight is doing the same thing, only it is being reflected like a raindrop that we saw in the bows. But this is called glory. And if any of you do any flying, anytime you're flying over water droplet clouds, you're quite likely to see a glory out there surrounding the anti-solar point, or exactly opposite the sun, around the airplane. And if you're close enough to the cloud layer, then the shadow of the airplane will show up. And I'll show you that in just a minute. But if you, hopefully on your computer, the picture is high enough quality here, looking through a highly scratched and dirty window of the airplane. That's another annoyance for us geeks who like to watch things out the window. Is the you can see these are the parallel lines of sunlight, basically, that are passing down, and the ones behind us, obviously the ones creating this effect here. Here we can see the condensation trail behind the aircraft. Can't quite tell what kind it is yet because we're still too far up, but we see that glory feature, or that coronal color, so to speak. Here's one from a small plane that I was flying, even though it may not look like it here. I'm down to only maybe 300 or 400 feet above the cloud layer, as thin as it is, because you can still see features below. There's the shadow of the aircraft and that glory event, and lo and behold, out here at about 22 to 24 degrees or so is what we call a cloud bow. It's not quite as circular because it's laid out on a flat surface instead of being kind of a perpendicular to us. Here's another cloud bow over the Pacific. Tend to be mostly white. And anytime we see a white bow, it means it's a reflection off of the drops or the crystals, with a little bit of color in here, indicating some refraction was taking place. Just a reminder of the drops and how they look, and when they freeze into crystalline growth. This is a chicken wire. I'll give you some dimension here, of about 1.5 inches, maybe 2 inches across, 2.5 inches from here to here. But what I want to do is show you the difference between what we call a rimed, that's R-I-M-E-D, or rime ice. It's a feature where it's kind of like the ice you have in your freezer unit of your refrigerator, and it sticks on the sides because of air that is passed into the freezer when you open the door. None of this kind of an ice feature will produce any kind of a color bow, because this frosty appearance is knocking down the light, of any surface that could bend the light and produce color. But on another occasion, that same chicken wire, but closed in here a little more, if you can see, hopefully you can, here's a six-sided, and the six-sided nature of these crystals owes its origin to the hydrogen and oxygen bond of those two to make a water molecule. Those two elements come together, and the way their electrons are shared, it makes this frozen bond show up in a six-sided orientation. And then over here you can see not as clearly any six sides, but that this is what we call a plate, and this is actually a six-sided plate that's sitting on another six-sided plate. And this one here is more an elongated, what we call a pencil crystal. And if you cut a portion of that pencil, you would wind up with a plate. And these are the primary shapes that are producing most of the arcs and the color features and reflected features that we see in the sky. Here's a drawing of a pencil crystal, again the 6 sides, and to get the 22-degree halo, and we'll show you that in just a few minutes here. It's where the light comes through one of these 6 sides here and comes out another 6 sides. And the net effect is that the difference in the direction is about 22 degrees. And that produces the most common halo that we see in the sky. And we'll show you next a plate crystal. And you can also get light coming in one of the 6 sides and out the other to also produce the 22-degree halo. But the brightest and best displays of color comes only when the light comes in the top or bottom of one of these plates or the end of one of those pencil crystals and passes through a 90-degree prism, so to speak, and spreads the beam further, and then we can see the distinctive colors better. Here again, this is a plate crystal, this is the pencil crystal. And of course, since they're in the air and falling at basically slow rates, and some of them are almost hardly falling at all, but they can be rotating either around their lengthy axis, or they can be spinning in this direction with one face remaining in the same position. This one can be rotating this way, or it can be tumbling. And so the most frequent position that this wants to be as it's falling is to be kind of flat, like this here at the bottom of the graph. And the pencil crystal wants to stay like this. And so anytime we get light that just reflects straight off of one of these clean, unrhymed features, then it brings light back towards us as we view. But if we have bending, then we have the colors. Here's an actual picture of a pencil crystal. And again, if we took and cut part of this off, then we would have one of those plate crystals. So here's your eye or mine, if we were looking out into the sky, seeing this photograph here. The sun straight in front of you, and it might be a good time to say, don't try to view these things, you know, with just no dark glasses or something to, because it'll overwhelm you. If you look for any length of time, of course, there's some damage to the eye, so we don't want you to do that. But if you got some dark glasses, or if you don't, get some, and it'll make it a whole lot easier. And particularly these things that you have to look towards the sun to see them, or get something that'll block the sun out for you, a tree limb, or your hand, or a lens cap, or something. But you can see here, if you follow this line here, it's bending through one 60-side face to another and coming on down to the eye, and that produces this 22. That's the number of degrees of a full circle away from the light source, or the sun in this case. So it's coming in this side here, bent 22 degrees to us, bent 22 degrees, and that's how we see it. Again, looking out through the edges of a plate crystal or the sides of a pencil crystal, the sun's here. And another little feature that most people call sundogs, these things have been appearing to mankind for thousands of years, and some of them have documented what they've seen even back to the time of the Babylonians, about 4,000 years ago, and even before that, I guess. And so these names obviously are different in Spanish and French and other places, but the Greek word, I think, is parhelion or parhelia for both of them, and that forms near the 22-degree halo, and we'll talk about that a little more in just a second. Pardon me. And we'll also talk about some other features here. This one shown here in this picture is the circumzenithal arc, and that's where some of our best colors show up. And I see I'm 35 minutes into this, so need to pick it up a little bit. Here is a picture, and I've dreamed of having a chance to go to Antarctica, or for anybody who might be watching from Alaska or northern states, North Dakota, something like that, you could see some of these with these whole field of crystals in the sky. This is the 22-degree halo here. The sun is here, and you can see that they blocked it out with a little wire with a disc on it. Then we have some additional features, these parhelic or sundogs here. This is what we call the parhelic circle. And if you notice, it is all white. So that tells you this is just reflected light. That is, it's coming into the crystal, reflected off the back of the crystal and back out to us. And if you have the sky full of crystals all the way around, that's kind of tough to see in North Carolina or Tennessee, because we generally don't have a full sky of crystals. They're so perfectly formed that we can see this. But again, it's kind of like that hula hoop that I talked about earlier, that this will go when the sun's elevation is pretty close to the Earth's surface, maybe only like 5 to 10 degrees. This will almost parallel all the way around behind you and come back the whole horizon, and that's why they call it circum, or around the horizon, the circumhorizontal arc or a parhelic circle. And then out here we have a more colored bow, which requires, again, 90-degree faces to be doing the refracting, and this is called the 46-degree halo. And connected, or in the opposite direction here, is that zenithal arc. There's also a horizontal arc that forms down here, but the sun's too low to be seen to see the circumhorizontal arc, but we'll show you a picture of that. And only once in my 50 years or so of viewing these features is to have seen this, what we call an infralateral arc, and it's a 90-degree face refraction requirement on this one, and the picture I'll show of this had none of these other features, only this arc was there by itself. And if you didn't know this, you'd really wonder what in the world in a sky with no raindrops that the thing would be sitting out to the side. Other arcs, this is called a tangent arc, and our early discoverer in 1819, 1820, looking for the Northwest Passage, discoverer by the name of Parry, P-A-R-R-Y, he saw for the first time, at least to be documented, was this arc up here, and so it's now called a Parry arc, and it's just another beautiful feature. Kind of makes this look like an eye, or an ellipse, or a flying saucer, or something in between there. And so let's go on a little further here. This is a picture where we're looking straight up in Antarctica at the South Pole. It'd be like laying on your back in the snow looking straight up, and the sun's down towards your feet. And here's a 22-degree halo, here's a 46-degree halo, here's a circumzenithal arc, here's a tangent arc, here's a Parry arc, some infralateral arcs out here, the sundogs, and the parhelic circle all the way around here, and then some what they call anthelic, or away from the sun, that is A-N-T-H-E-L-I-C, anthelic arcs that are a little different and more in a kind of a raindrop appearance, and they cross the parhelic circle clear back here directly away from the sun. That would be up above your head or behind your head as you were laying there on the ground. And it's just incredible the number of things that can be seen out there. Here's a 22-degree halo, again with a refraction The red wavelength is on the inside. Most of the rest of this, because it's only going through that 22-degree face refraction, you don't get a great color beam here because you're not making it distinct enough to be seen by the human eye. Here's the one at nighttime. This is my wind tower where I took that first photo that I showed you from western North Carolina. This is a tangent arc, and a little bit of the sundogs or moon dogs in this case sitting out here, and I'll talk a little more about that in a minute as to why they're not connected to where the 22-degree halo is, as we saw in others. You can see this from the airplanes. It's kind of neat to think that you're flying along at 500, 600 miles an hour, and the bow stays right with you, because each crystal that comes through that proper position at 22 degrees off the sun will produce that color as we see here. Here's a close-up of the tangent arc, 22-degree halo here, and the peri arc sitting up here above it. I did not take this picture. I wish I could say I did, but it shows an example of some of these other things that are going on. And this is a feature I've never seen before called a Moilanen, one of our Scandinavian sky watchers, with the 22-degree halo again. And then here, as the sun lowers, these tangent arcs that showed over my house was more flat. The lower the sun or moon elevation, the more this thing turns upward. Then we have the peri arc is also now turned upward, and so they call that a sun vex, or away from the sun. Here's another arc which is quite weak, but this would be the sun cave, or curved towards the light source. 46-degree halo. There's also something called the superlateral arcs, which are quite weak but can barely be seen in this one and the circumzenithal. Now these folks up here, they could never see a circumhorizontal arc that far north because the sun never gets far enough above the horizon for it to be seen. This is called a sun pillar, and we'll also look at that in just a minute. Here's the best example that I've ever had of a sun vex peri arc, which is right above the sun after it's actually gone below the horizon. Just a neat feature. And here's something that I had observed but never knew why, that at the low sun angles, the parhelia or the sundogs are right on the 22-degree halo. We go up to 10 degrees above the horizon. They're still there. At 20 degrees, they're separating a little bit from the 22-degree halo. At 30 degrees, even further. And at 40 degrees, clear out here. That again is kind of that hula hoop process, that as you tip the hula hoop up from a horizontal position, it becomes a more of a circular than when you have it perpendicular to you as you were looking towards the sun. So just another neat feature, and we'll show you some examples of that. Here I've used a road sign to block out the sun. And here at that low sun angle, just above the horizon, so to speak, maybe 10 degrees, we have our sundogs or parhelia right there. And of course this bright extension is because of, and being white in color, we have the reflection going on in those crystals on that parhelic circle that we talked about earlier. This is a real nice strip of brightness, brighter than anything in the sky other than the sun source itself. But the 22-degree halo, it's about 40 degrees above the horizon here, so we see we've got our sundogs separated by maybe 3 or 4 degrees from the 22-degree halo. Here's another one on the other side, and you can see a longer extension of the parhelic circle. And here's another one. We're actually looking almost exactly away from the sun now, and here's the backside of that big circle of reflected white light. Again, no refraction here that appears in the clouds, but you can also see that it's brighter in some portions of the cloud than the others because of whether they are good clean-faced crystals or whether they have any rime that might impede that reflective light. And if you remember the anthelix arcs that cross this, you can't see them here, but we know they're there because exactly at the opposite position from wherever the sun is, we've got this bright spot where the crystals are all in an orientation that maximizes the reflection of the light back to the observer. And just neat stuff. Now, if you remember, I told you that as the sun gets higher in the sky, the parhelix circle begins to bend in a steeper arc. And if you go even further, this arc diameter gets smaller and smaller. And one day when I happened to be home, I saw that the sun was sunlight on the grass was a bit muted, and I said, well, maybe there's something to see out there. And I looked out, stepped out on the deck, and here's the parhelix circle, almost the same diameter as the 22-degree halo. And the simulations that can be done on computers shows that if you saw this feature somewhere near the equator, that the parhelix circle would actually be a circle going through the sun still. See, the halo always is circling the sun. This goes through the sun and out and around, but say 5 degrees north or south of the equator, and this parhelix circle will have shrunk to the point of actually being inside the 22-degree halo. And unfortunately, the 3 or 4 times I've been near the equator on mission trips, I never got to see it, and I was hoping that I could. Okay, we're going to move forward here into another portion of the arc phenomena, and this is simply light reflecting off of a surface. And when these crystals fall, again, quite often the best crystals that are out there to do some of these features are ones that have fallen from these super cool clouds and have no rhyming on them, to where they're just clear like crystal that you would buy at a Swarovski store or something like that, with no dirtiness or anything, just a clean face. And so these are just reflections of the sunbeam, just like the water was in the previous picture, and they can appear above or below the sun. But those same crystals also generally make good parhelia or 22-degree halos sitting out here to the side. Here's one over the Sahara Desert. See, some of the Sahara desert dust has risen to about 20,000 feet elevation. We're at about 37,000 taking the picture here. And down towards the bottom of the picture, you can see a little bit of the 22-degree halo. So again, the same thing that does one feature, kind of look around, there might see something else that goes with it. And this feature is called a sun pillar, which is kind of makes sense. Again, best crystals, ones that are falling from alpha cumulus that are not rhymed. We also see something called a subsun when we're flying. You could not see this feature very easily on the ground. And again, off to the side, we see a little bit of parhelix, on the parhelix circle, a little bit of a sundog. And so keep your eyes open for that. And this, of course, moves along with the aircraft at whatever speed you're going. This is over Afghanistan, I think, on our way to India. There's another one here over Colorado. And again, reflection off of the faces of these clean crystals. Just kind of for reminders here of what we're looking at. In this case, a 22-degree halo, which is not all that bright, with a little bit of a peri arc up here, and a little bit of sundog brightness off to the side here. And out here at 46 degrees away from the sun, almost twice as far out in radius as the 22. And that infralateral arc that I was telling you about that I've only seen once appeared relative to this photograph here in this position here. Let's take a look without the arrows on it. And again, this is refraction through 90-degree faces. This is refraction through 60-degree faces or sides of those crystals. So the next one is the infralateral arc. And here it is with the blues and the yellows and the green and the red showing up in these crystals. And typically, if you're looking to say, well, am I going to have anything to see once these crystals, if they're moving across the sky, the ones that are the least white will often be your best producers of color, because they're unrimed and they don't bring as much light towards us as one that has been rimed. Here's just a multiple feature. Again, the circumzenithal arc, and that is strictly from those 90-degree face interactions with the sunbeam. Here's a tangent arc, the peri arc, 22-degree halo, and part of the parhelix circle with a sundog at that intersection. Here's another one here, quite nice. You see, these are quite limited in their whiteness, but a good section of a zenithal arc up here. Don't see the 46-degree halo, probably because we don't have a full sky or even a portion that would produce that. 22-degree halo, upper tangent arc, peri arc, parhelix circle, sundogs, and cool stuff. The zenithal arc by itself, another one. These were good clean face crystals here. And so when I saw them falling out of the altocumulus cloud to the west, and they were moving this way, I said, looks like we got a chance. And about 15 minutes later, when they got into the right position, about 46 degrees from the sun, there it was. Old contrails, sometimes those are unrimed crystals, and they can be good producers of color when they come through that same position. Now here's the only decent circumhorizontal arc positions, and this is basically at the bottom of that 46-degree halo, but the sun has to be at least 68 degrees above the horizon, 58 degrees above the horizon before you can see this, because it just otherwise it would appear somewhere down here where we can't see it. So the zenithal arcs that are above the sun are something you're going to most likely see in the wintertime. The horizontal arcs are the ones you see in the summertime, but since we here in the southeast we have bad visibilities that time of year, if they do form, you're only going to see kind of a milked out feature. Just a little closer view of that. Pardon me. The best horizontal arc I've ever seen was 35,000 feet over the Mediterranean on that same trip when we were headed to Tanzania. And it was just by the fact that we're up there in clean air, and this I considered another blessing. This existed sometimes dimmer, sometimes brighter, for a period of 20 minutes at 550 miles an hour across the landscape, and it was so amazing to know that the crystals are whizzing by, and yet at that perfect point relative to the sun, they're producing this beautiful beautiful horizontal arc. And that's the end of the arc part of this presentation, and very quickly I'm going to go through just a couple of other things that I hope you will enjoy. Some of you may not be old enough to remember anything after, or certainly at 1982, when a Mexican volcano blew up and put some material in the sky for 2 years into the stratosphere. This is what a clear night looked from our deck, looking southwest, wintertime, nice clean air, blues to yellows to oranges. And the next one was taken after, about a year after that volcanic eruption. And the clear night sunsets continued like that for another year. It was just quite pretty, but it certainly changed the appearance of the sky for quite some time. Crepuscular rays, something describing these beam effects we have here, and it's their spreading is actually the way our eyes view it. They're actually parallel, but just like railroad tracks, the further they get from you, due to what we say perspective, or the eye's ability to distinguish things at a distance, makes them look like they come together at a point. And the word is crepuscular. I did not name it myself. It's spelled C-R-E-P-U-S-C-U-L-A-R. But they can produce some gorgeous effects from behind some towering cumulus clouds here. And here's one I shot here in East Tennessee from my home where we live now. And all that's going on here is that in the darker elements here, somewhere in the distance, and right here we can see that this cloud is stopping enough sunlight to where there's less light to reflect off of the haze that's in the air. So where the beam is strong, it'll be whiter. Here's one from the air. Again, light beams coming through the openings between these towering cumulus clouds. And kind of keep that in mind. I'm going to tell you another little story here in a few seconds. Here's one over the Panama Canal at 35,000 feet. And these towers are probably 100 to maybe 200 miles away. So they are blocking the light at a great distance, but we can still see it in the haze of the upper atmosphere. Here's one was taken by somebody appeared in the Chicago newspaper, and this particular event, they saw these kinds of beam effects from Chicago south to Springfield, over 100 miles. So I was fascinated by the great distance of horizontal distance that this appeared. So I decided to look at the satellite imagery. Here's Chicago where the picture was taken, but it was seen all the way down here. And about 200 miles to the west, maybe 150 miles, that same evening we had a line of broken, small, towering cumulus clouds along a prefrontal boundary. And they were the little things that were causing these shadows to show up all the way over to Chicago down to Springfield. Neat stuff. And in the opposite direction, if you happen to be standing near the items that are blocking the light, then we see the rays meeting in the distance, and these are what we call anti-crepuscular rays. And a friend of mine took this picture over the Rockies, northwest of Colorado there, and you can see them coming to a point in the distance. And he was so fascinated, he says, I couldn't believe this, and he was describing the effect, and I said, yeah, I think I know what you were seeing, but the picture is a great example of whatever. And one of the last items we'll talk about here is mirages. You do not have to be in the desert to see it. Anytime you have a strong change of temperature with height, produces basically a mirror effect of light rays, and can cause them to change direction. Most often it is certainly over hot regions And sometimes, though, over cold, like Lake Tahoe, you can see very low-level inversions when you look towards the other shore. So you don't have to be on a desert, but certainly that's where many people refer to it in terms of the mirage and that water source or whatever you might have been looking for on your camel train. The next picture I'm going to show you was, this is the normal view of the mountains with full mixed of the atmosphere mixing. The next one, the same mountains under the effects of a mirage, and the temperature inversion is right across through here. So instead of a peak over here, we now have a plateau or a mesa. Look, and for a while it almost looked like this is going to build a bridge all the way from this peak to this one. And looking in the opposite direction to the southwest, on the same day and same morning, we saw some other funny effects. When you're used to seeing individual peaks in this part of the country, to see these flat top features, it certainly catches your eye. And back here is a totally artificial feature from a very distant peak that was showing up in some other portions of that temperature inversion. This was a rocket experiment that the Air Force did out of Eglin Air Force Base in North Florida back in December 1980, and I was told by some friends that the law enforcement phone bank lit up that night. They were testing some elements of barium and other things to see if they could produce basically an artificial aurora and try to study how that takes place and the stretching of that over time. We, in western North Carolina and other places further south than certainly the Canadian border and other places, you can see in great solar events the Aurora Borealis. This one was in March 13, 1989. And I understand last month's webinar was with a man whose name escapes me at the moment, but he had some fabulous pictures, and these are not to be in competition with his, but it was really interesting. This one was seen as far south as Jamaica when it finished up down over the Gulf Coast, and this is the same event that put, through the induction surges on the power lines, put about half of New England and a third of Canada out of power because it burned out the transformers. But being away from the city lights, it afforded us a great opportunity. This is looking south to see the northern lights, and that's where it finished. That was 1989, and then we had probably one of the most beautiful features in March 24, 1991, on a two-night event. This is looking over Black Mountain, North Carolina. And one of the other interesting things is we know that the magnetic lines come together and focus into the magnetic north and south pole. We're blessed, at least for aviation purposes, that from western North Carolina and East Tennessee, essentially the North Pole and the magnetic North Pole, that is geographic and magnetic North Poles, are almost lined up perfectly north. We're now looking northeast, and you see the lines of the current coming into the upper atmosphere is kind of cantered at about maybe 20-25 degrees from straight up and down. The next picture, the following night, the greatest part of the formation was due north, and you'll notice the lines are almost exactly straight up and down. And that was, I shed a tear that night. I've never seen anything more beautiful in my life. And just to give you a thrill here, the aurora does occur on other planets as well. And this is Saturn. And I'll just skip to that one and say thank you for your attention. I hope you've had a little fun. And I will take it off at this point and end that show, and back to you, Henry.
Well, thank you, Grant. That was a fascinating presentation. Wow, some beautiful photographs there. We really appreciate that. Hey, we've got some questions coming in. If you guys would like to type in your questions now, we'll try to take them for the next 15 minutes or so. And those which we aren't able to answer on the air, Grant will follow up with you shortly. Somebody wrote in, want to know what kind of photographic equipment that you've used on these.
I appreciate that question. I had meant to mention during the presentation, most of the, I'd say 98% of these photos was taken with a film camera. I used Kodachrome 25 for decades until Fuji 50 came along in somewhere in the 80s, I think, and I saw a presentation where each film was used in identical cameras, like fall colors, the sky, and so forth, and Fuji just seemed to do better. And so it was just a medium cost Pentax camera, but I did spend a few dollars on the lenses. If you want to see those pictures of, say, the full sky, see if I can get back to it here, something like that, you've got to have something at least of on the order of 17 millimeters, and even wider for a digital lens, since the sensing part of a digital camera is a different dimension than a film camera, as it's smaller. Then you need like a 10 millimeter lens to be able to get all of these arcs in one picture. But Pentax, right now I'm using a Canon EOS, and I got a 10 millimeter lens for that one to be able to get some of these features, or if you're taking pictures of clouds, to get a full sky view, you just need something wider than 28 millimeter or 35, which kind of was considered a wide angle lens, but for some photos you want more of a telephoto to get a tight shot of, say, a parheli or something. You can use standard and telephoto lenses to do that, but most of the pictures that you've seen here are electronic versions of a film image.
Thanks, Grant. We have a question here for actually Tiffany from NASA is on the talk today, and she wanted to know, do the tangent arcs only occur in the high latitude areas?
No, you can see the upper tangent arc, and they are the ones that are most visible, most frequent. You can see them pretty much at any elevation, particularly in an early morning or a late evening. Your sun's going to be down to where it's not hard to see. But the lower tangent arc, which I didn't have any image here to show you, it is much more difficult to see, particularly at these latitudes, because of the element of pollution again. But in the, say, northwest territories of Canada or Alaska or Antarctica, then those other features are not compromised in that manner, and you can see both the upper tangent and the lower tangent arc.
Thanks, Grant. Chuck from Washington State wants to know, have you ever seen moonbows?
I think I did, but as I recall, I didn't have a camera at the time. That's something else. Us geeks, you almost have to have one hanging around your neck or in your pocket or something at all times, because probably the most brilliant horizontal or circumhorizontal arc that I'd seen, certainly before the one over the wing of the 767 there, was one day when I looked at the sky and the forecast and said, I don't think I need to take the camera to work. I walked out the east door of the old arcade building there in Asheville and looked south, and this, it just blew me away. I turned around and went back in the building. I couldn't stand to look at it any longer and know that I didn't have my camera.
Okay, I've got another one. Carol wants to know if you use a polarizer filter. She's from North Carolina.
Right. No, I know that they would help in many of these photos, either because I was too cheap or something, that I just never got one for my film camera. And but I, having seen them and seen examples of what they can do, particularly in haze, that is certainly something that can greatly, you know, make your pictures clearer. And one of the other things I might just throw in is to, even without the polarizer, the best thing is, if you have the ability, is to underexpose the image several stops to bring that color out. And now, even if you don't, with the capabilities of some of these electronic adjustments that you can make, just as fabulous to bring out color in detail that you would have never seen otherwise.
And I have someone here asking, what focal length lens do you use to get the most of the sky in the photo? So,
well, the widest thing that I've seen for the Canon EOS is that 10. It's like a 10 to an 18 that I have, but it's somewhere between $750 and $800. I mean, it costs twice as much as the camera. But that's to get, say, 80% of the sky. It's got to be at least a 10 millimeter, and with the film camera, it took something wider than that to get full sky. But this, I think, a 10 millimeter covers something like 100 and well, I can't even remember. 190 degrees or something of the full horizon.
okay, here's one. Actually, looks like a friend of yours, Andy Goss, writes in. He wanted to let you know that he was on the Alaska Marine Ferry this September and saw a fog bow several times. You want to explain what those are to folks?
Yep. Hello to Andy, and glad to know he's doing well. Yeah, I took with my wife and some other family members a cruise to the inside passages this year, and we got into a fog bank on our way back from that cruise, and coming in between British Columbia and the Olympic Park and Straits of Juan de Fuca, I guess, and went up on the bridge and had all my lenses and everything, and never could get it just, for whatever reason, just couldn't find a bow in that fog. But it's basically very similar to that glory effect that we saw where I was standing looking off the side of the hill. But it's a wider bow than that particular shot that I had. But I've seen the fog bows off the side of the mountain, but just couldn't get a good one off the bridge of the ship.
Okay, Rick writes in, and this is more of a CoCoRaHS question. He wants to know, are there CoCoRaHS volunteers that count and record the number of rainbows and send the results to CoCoRaHS? We're not collecting them at this time, but you can always put that information in your comments field, and we do look at that. So thanks, Rick, for that question.
I appreciate him bringing that up. And something else, there's just so many things that I think about as I go through these things, is that in the old days being something at least 50 years ago, and of course in the last 20 years we've lost that kind of information because of the automatic sensors, instead of having observers at the airports or city offices or whatever. but I'd say from the institution of the Weather Service in 1880, 1890 time frame up through the 1950s, that was part of the requirements of the observer, was to mention certainly halos and other sky features like that, and even earthquakes, which are not a sky feature, but
sure,
they were total observers.
Mike writes in, and he's from Ohio. He recommends a book called Light and Color in the Open Air by the last name of the author is Minnaert. Grant's got a list of books as well. We'll list these on our web page for you, so you can go back and take a look, and just to give you a listing of all optic books, that'll be helpful. So give us a couple days.
Thanks for thanking for that reference.
I appreciate that there, Mike. Okay, a couple more questions as we round things out here. Alan wants to know, is the color of clouds as a storm approaches an indication of how much rain is in the cloud system?
Woo. I'm not sure if I would describe it as color, but I would say that the less light, let's say in the case of an approaching thunderstorm, the less light that can be seen, the denser the cloud is, and also the taller the cloud is. And some of the lightning safety talks that I do is that when you can't, if the storm is right overhead, or let's say you're in a forest or something and you can't see the margins or the height of the cloud and so forth and say, wow, this thing is really cranked up, the best way to determine whether the cloud is continuing to develop is that the base of the cloud gets progressively darker, and the darker it gets, the less light, the taller the cloud, and the more obstruction of light is taking place, and that the likely potential for certainly lightning to develop in that storm, but also that there could be heavy rain, depending upon, it's kind of a very slow mover. It could bring flash flooding, but the worst thing, danger for human activities is the lightning.
Thanks, Grant. Appreciate that. Got a couple more questions here. Let's see. Richard wants to know if you could redefine quickly for him sundogs. I think he'd like to find out what those are again.
Basically, it's a colloquial name, and I am digging through all my texts here. I could not find something that referenced the origin of the term. Henry and I had talked about it a couple of days ago, and I just hadn't been able to find it. So I didn't go to the web. It may be out there. But it's basically is a colloquial name for that brighter segment where the parhelix circle intersects the 22-degree halo, and basically and I didn't say this during the talk, is as these crystals, whether they be a flat plate or that longer pencil crystal, as they fall, the closer they get to the horizon or wherever the sun is, and the lower the sun is, then you have a maximization of the light from the sun. That is, those sundogs will basically, even though they may not be touching the 22-degree halo and stretch out a bit, the higher the sun angle above, that is, the sun is above the horizon, the sundogs will always be, you could draw a straight line between them and the sun sundog on the other side. So even though they may move in or out to the 22-degree halo, they will always remain in the position of the sun, and that is because we get the most number of crystals that are giving us that reflected light and refracted light to the observer. And so they, it's kind of like having a mirror out there, and if that mirror is facing us in a position, then it produces a greater light than if it was tilted to some angle away from us. I'm rambling a bit there, but I appreciate the question, and sorry I didn't address it earlier.
Okay, we got our final question of the day, and actually it's two questions, one from David and one from Nancy, and they're just about the same. David wanted to know, do rainbows appear only during certain times of day? And then Nancy wanted to know, she lives in western Colorado, which direction should she look at what time of day to maximize her chance of viewing these phenomena? And she didn't explain which phenomena, but see if we can take a look at that.
For the lady in Colorado, I'm not sure how, if you're down deep in one of those beautiful valleys out there, and I do love that state and the visits I've had out there. I don't know how much the mountains may obscure you. Maybe you're out on the plains east of Denver. I would say certainly to see the rainbow is most likely you're going to be looking to the east, because most of your shower activity will take place in the afternoon hours, and certainly you get a lot of them at nighttime, and then forget about the rainbows at that time. So you'd want to be looking away from the west and looking towards the east, or east-northeast, east-southeast, depending upon the time of year. But most of the shower activity is afternoon hour, except, say, when a front might have passed, you might have the rain ending and the sunlight coming out, and that could be either in the morning or in the evening. So, but I'd say your highest number would be towards the east. Getting back to viewing some of these things, you can see a halo any time of day. Only a half of it, of course, when the sun's getting down to maybe 5-10 degrees above the horizon, but it can be straight overhead. But there will be a lot of days when you see cirrus, those ice crystal clouds up there at 25, 30, 35, 40,000 feet. And they're all rhymed, and there's not even a hint of any kind of a bow or an arc or a halo. But just keep checking, and just pan the whole sky, and you're likely to see something. The zenithal arc, which is the brightest one, just look when the sun's low in the sky, look almost overhead, thus the name zenithal, up at the zenith or the top of the celestial dome, and you just may see one.
Well, Grant, thank you so much for being with us today. I really enjoyed your presentation, and thanks for all you've done over the years. We really appreciate you.
Thanks, Henry, and thank you to everybody who was listening today, and hopefully you got a feeling from my words that to me this is a gift beyond many things that we can buy, and I thank the Lord that He's given me the eyesight to see these things.
Well, folks, please join us again next month for our next CoCoRaHS WxTalk webinar. That'll be on December 13th, a Thursday, at 1 p.m. Eastern, and it will feature Paul Cosin, formerly of the Weather Channel, Winter Storm Desk. Paul's now with NOAA's Hydrological Prediction Center, and he's going to talk about historic snowstorms. So that should be a very interesting talk with a lot of examples. We look forward to that. Finally, before you sign off today, please take a look at the survey at the end of the webinar, and if you could fill that out. So until next time, this is Henry Regis for the CoCoRaHS headquarters crew, signing off and wishing you well.
Thanks.
Bye-bye.